Okay. That way, for anyone who does miss it, we can let them know what it's supposed to be. But what was I saying now? Oh, section 8 really leads into section 9, which then will lead into section 10, section 11. I think those ones flow very naturally into each other. So section 8, as you end it, you'll see you'll start doing more probability, and then it ends up being the binomial distribution. And then after the binomial distribution, you'll actually go into section 9, and section 9 is about distributions. And this will actually lead us into hypothesis testing, which kind of relates to how we do linear regression, because linear regression is basically we're making these models, trying to figure out how these, basically trying to do predictions. And section 11 basically is a continuation from linear regression, particularly multivariable, multiple linear regression versus simple linear regression. So that's kind of like this pathway of what we're doing going forward. So I'm going to go right into this because last time I did, what's it called? Statistical distributions. It ended up going, I didn't quite get through everything I wanted to. So I want to make sure to kind of get through parts that we need. Hey, Yasmin. Okay, so let me go ahead and share my screen, which I'm getting a little bit faster now. I spoke too soon. Okay, cool. Can you guys all see my screen? Cool, all right, awesome. I wonder if I can put you guys don't see you right now, right? Like, okay, good. I want to make sure I wasn't blocking you guys with my thing, because you guys will give me thumbs up or something, or I see someone unmute and ask questions, and I don't see you guys. Have to look off to the side here. So, okay. So if you guys want to, and I'll basically share this guy out so then you guys can follow along. You can edit it, which means you can run stuff and what's it called? Kind of play around with it. You can, maybe don't do it too much while we're talking about it, but I mean, you're welcome to try it out, or if you guys want to kind of code along or say, hey, can we do it this way? You can just write it right there. So anyway, there's the link in the Zoom chat. But what we're going to talk about is statistical distributions. So statistical distributions will lead us right into basically how we visualize data. And I really like saying that, like, when we do data, what we're really doing is trying to figure out how to summarize a vast amount of information. Because you think about it, when we have like 20,000 data points, like all those data points are unique individual snowflakes that we all care about and see exactly what it is. They each have their own little story behind them. But we can't look at every single one. 20,000 is a low number. You might have literally millions or even billions of data points, and you just can't have the time to figure out. That's where basically we'll go into statistics, and statistics will basically allow us to summarize this information. And that's really great, but just also know in the back of your mind is whenever we're doing anything like, essentially a statistic distribution, we're by its nature trying to summarize and get rid of some of the information so we can better visualize what's going on. And you'll hear me say this again and again, is that I firmly believe that doing visuals can be really key to doing analysis. And I think part of that reason why is because humans are just generally just a visual species. Like, we're very good at visualizing things. We're very good at finding patterns in visuals. So plotting out distributions, plotting out scatter plots and stuff like that helps us identify those patterns. And they're not going to tell us the answer. They're not going to tell us like specific information that we can use, like quantitative information, but it can help guide us and basically kind of give us hunches saying, hey, this looks kind of weird, or hey, this looks kind of fishy, or, what if I transform this and investigate it a little bit more? That's the kind of stuff that you want to do for visuals, and distributions are particularly useful for this kind of thing that we're doing. Okay, so jumping into it, showing distribution. These are the general, you guys probably seen this on now. We have our general, it's called our different imports that we have. So of course, pandas, seaborn is our kind of extension to Matplotlib. Of course, Matplotlib, which is notorious for all of its different things we can have. We might use this part, I actually don't know if I call this, but SciPy, kind of related to like how we use NumPy. It's another package with a lot of really great like numerical like extensions, like functions that we can use, and particularly you can use it for stats. In this case, we're importing just skew norm, which allows us to basically do something about the skew. But anyway, excuse me. So in a distribution, we're basically taking information all from some data. And in this case, you can kind of see a quick demonstration. It's like, okay, I'm reading in data. Doesn't really matter what this is, but I'm reading in some information, some data, California housing test. And I can get like, you know, for example, the housing or the median age. I can get the mu right here, which is our average for that population, and our sigma, our standard deviation. So actually, I'm trying to remember now. Who's familiar with standard deviation? Just give them a little quick thumbs up if you've seen that before. Maybe give me a thumbs down if you're kind of like, or sideways, like, I don't really remember what that is. I think we talked about this, right? So maybe a little bit, okay. Okay, so we'll talk about it a little bit more. But these are big parts. Is basically what's it called? The median, the mean, and standard deviation, or I should say sample standard deviation. Those three tend to be very, very important stuff because it helps to find basically how our distribution looks. It gives us a quick summary of the data. Okay, so I believe we run these now, and hopefully, no, I don't have my file. I don't know why my file's not here. Okay, that's okay. We don't need the file. I had a feeling this is what happened from before. Okay, so we're gonna go straight into statistical distributions. So the first thing that you'll introduce in the curriculum is a probability mass function. And your probability mass function, the reason I call it mass, okay, it's kind of like handles on, or it's like weights hanging on a bar. So you can see that PMF will be very close to a histogram. And so this right here is just taken directly from the curriculum. This is our probability mass function. You also hear me say PMF. You'll see abbreviated PMF. You're going to see a lot of distributions just abbreviated this way, just so we don't have to call probability mass function that long, long way. But you can kind of see is that what's happening is concentrated into certain segments. And this is actually very similar to a histogram. You can imagine, for example, us making little bars here. But note that on the side here, it is not actually the count, because in the histogram, we're actually measuring the frequency. We're measuring how many times does this value occur, or at least this value within the range. So if we went like from like, 1980 to 1990, you might have like, 20 occurrences in that range. This right here is instead doing our probability. And our probability comes from the fact that, our probability comes from the fact of number of different events that we have. So essentially, if we have these parts, all this, is anyone got to guess if I added up all of these values at these points, if I add them all together, what number we'd get? Yeah, see Yasmin go 1, right? So I used to have I don't know if I talked to you about this, but I used to have a physics professor who said back when they were in undergraduate, they would have, him and his friend would always just guess whenever said, oh, what do you think it is? They would always say 1 or 0, because usually it's one of those two. And then I guess you could go infinity, but we probably won't have infinity that too often. So anyway, probability mass function is basically a scaled histogram. And essentially what's happening is like if it's saying how often these events occur. So I can show you a quick coding example. Okay, so I'll kind of walk through this part a little bit. So we did our imports right here. This is actually taken direct, I think it might be a modified version that I took from curriculum. So we have the imports from Matplotlib. We have collections, which basically allows us to do certain, because it's another package that allows us to do some quick calculation. Okay, so we're going to simulate rolling a die. And so in this case, from rolling a die, or say rolling one die, is np random.randint. And this allows us to randomly choose between 1 and 7, this low and high, okay? And we're gonna roll it 30 times, okay? Same thing for die number 2, we're gonna randomly roll it 30 times, okay? And we can see the sum of the dice. So I'm actually gonna comment this part out so we can see this first part. And we can see that we have here the roll of the dice going from 1 to 7. And I should have noted that this 7 here doesn't actually get counted. So only 1, 2, 3, 4, 5, 6, not including 7. So you can see I can roll this. In fact, I can roll it multiple times and you can see that these numbers will differ, okay? And in this case, because it's random, it's actually uniformly random, which means that every number is just as likely. So I'm just as likely to roll a 1, a 5, a 4, a 3, a 2, whatever, right? Sometimes it'll happen more frequently, just like real dice. Sometimes you'll roll a bunch of times and you'll get 6, 6, 6, 6, always like constantly, or like, what the heck? That's just random, right? So I got these dice and I did this little sum right here so we can see that distribution. And so afterwards, I have a counter die. So this bit of code right here, has anyone got an idea what this code does, just kind of reading collections, counter, and kind of passing it with full die. And got to guess. And this one is good if you see code that you've never seen before. Any wild guess? I see you, Joshua.
So, I guess how many times how many items are in the collection?
Good. That's exactly it. It counts how many times you rolled a 5, how many times you rolled a 3, how many times you rolled a 4. Okay. So it's counting basically in that list, right? I should say array, but anyway, it's counting how many times that happens in that array. So in this case, if 5 happens 5 times, you'll see basically it's a dictionary, it turns out. 5:5, meaning that 5 was rolled 5 times. If it was rolled only 2 times, you say 5:2. If 5 never appears, what do you think that shows up in the dictionary as? Anyone got a guess? I see Yasmin go 0. Yeah, turns out it won't show up at all because it never happened, so it doesn't know to count it. So something to kind of keep track. So if I probably did this for a smaller number, so oops. Let's just run this. So you can see right here, my list of events coming from here, the sum of the dice. And basically I'm doing that sum of dice and I'm doing the counter sum right here. I print the counter sum. So these are all the 7, 10, 7, 12, 7, 9, 6. And I basically just added these 2 parts, 4 and 3, 5 and 5, 5 and 5, 2 and 5, 6 and 6, 1 and 6, 5 and 4, so on. So you can see all the different sums they are, right? And I printed out the counter right here, and you can see the counter, okay? 10 happened 5 times, 7 happened 4 times, 4 happened 4 times, 5 happened 4 times, blah, 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 blah. And you can see, let's see here, I'm trying to find a good number. Well, first of all, 1 never shows up. It shouldn't show up, right? And you can see in here, there never is a key that is actually 1, because it never showed up in our distribution. If I had a smaller random set, and I think we hit every number in this case, but if I had a smaller, if I had like maybe 10 rolls of dice, I might not hit every single sum. I might hit only some of them in my sum. So anyway, this part right here now, I kind of preemptively put this together, is we're going to make a plot of this. And so I'll let you guys kind of look at that code a little bit later. You can check that out. But basically what I'm doing is I'm going through each part of the plot range, 1 through 13, all the possibilities. Turns out 1's never going to happen. It only goes up to 12, so that's why it's 13 here. So basically 1 through 12, and I'm going to put those on as my points. And I'm going to say, okay, get, for example, if 10 happened, okay, get 10, and then say, okay, how many times that is, divide by the total number of rolls in the die. In that case, it's going to be 30. So I get a probability. Note that I do a dot get here. And the reason why is because if, for example, 1 never happened, or, let's say I never rolled a 7, a total 7, what would happen in the dictionary, if I try getting that 7, it will end up giving me an error. It says, whoa, I don't know what's in there. So doing a dictionary counter die 1 is a dictionary. If I do dot get, it allows me to pick things out that aren't there. And if it says, hey, that doesn't exist, that's what that comma 0 is. It says, oh, use this default value, 0, which makes sense. If it's not there, in this case, we want to count it as 0. So this can be really useful when you're trying to iterate through a dictionary, or not a dictionary, through a list and using a dictionary. Or no, I'm the right first time. Iterating through a dictionary to get values that don't exist there. Okay. Any quick questions about this? What I'm doing? Okay. So basically, I'm just rolling the die, summing it up, and seeing how many times that happens, and just using the code to get this part. And I preemptively am using this part so we can plot it out. So, oh, someone have a question? No? Okay. So I have my plots here, and I'm going to plot this out, and we can see now we have a probability mass function. So you can see, for example, 1 never happens, right? And we see here 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can see I have the probability here. I also made a little histogram. So we have our stem plot, which again, curriculum kind of talks about this a little bit more. But I'm using that plot range to go from 1 through 12. PMF sum, which was defined up here. I'm just adding up all the times it happened. Okay. And so I get this probability. If I did a histogram of the same thing, you can see that I actually have it's just kind of shifted because it's a bar, but you can see I actually have that same shape going on here. But the difference is that on the y-axis, this is the this is the probability of it happening. This is the frequency. So if I actually ran this whole thing again, so if I ran another random set, in this case I ran 30 again, and I plot it one more time, you can see I get a different distribution. In this case, we never got a 3. We never rolled a total 3. And you can see here, these are about equal. So if I did this over and over again, you might see, okay, like you might do multiple parts. Does anyone know what the distribution for multiple dice rolls? If I kept rolling like a bunch of dice, what kind of thing we'd see? It's all right. I'm just jumping ahead and seeing if anyone know. So I'm going to run it 300 times, right? And you actually see it goes more and more into this nice little curve right here. In fact, if I do it even more, let's do 3,000. Actually, don't know if this will crash or anything like that. No, okay, we're good still. And you can see I get this nice curve going on here. And as I do more and more examples, eventually that curve will get nice and smooth because it's just random. And it turns out this is something called a bell curve, which we'll talk about towards the end of this. But this guy right here, our bell curve or our normal curve, or a Gaussian curve, you'll hear it talk about a lot, has this nice smooth picture. And we as data scientists, statisticians love bell curves because it means the math's nice and easy for us to deal with. Not everything's a bell curve. Things tend to go towards a bell curve. We'll talk about it in the future. Okay, so that leaves us to cumulative distribution. Yeah, I can't talk today. Cumulative distribution functions, or CDFs, right? So it's kind of the same similar thing when we're going to be looking at PMFs, which are these are our PMFs right here. But sometimes we want to say, you know what, if we have like a lot of possibilities, like imagine if like instead of having a 6-sided die, we had something that was like, I don't know, a 100-sided die, and then adding up those parts and all the different possibilities for the 100-sided die, it'd be really hard to see those bars. So cumulative distribution functions allow us to kind of visualize what they look like. So it's using the same information as a PMF, but the CDF allows us to kind of better visualize it. You remember our whole point of doing these visualizations, so we as humans can kind of see if there's a pattern that's hiding in there. So I'll show you what those look like. But basically you can think of like this length, this height, like we saw for the stem leaf with the PMF. It's just adding up everything previously. It's cumulatively adding it up. So I'll show you what that looks like. So this is our cumulative step function right here. So you can basically see is that, okay, as we kind of go through, only, let's say, what's that first part? Only about 0.03, yeah, 0.03 comes up here, or about 3% of the time. So it comes up here. And then when we get to 2, we add up, I'm sorry, not 2. When we go to 3, we add up this probability plus this probability, and we do that step up. So this will eventually go all the way, add up all the way up to 1, since that includes all the events. And we can see when it goes up really high like this, it means that there was a huge spike in the probability. So for example, you can see right here, going from 6 to 7, you can see the probability went up significantly. And you can see there's a much bigger step coming up from right here, from 6 to 7. So this can help us visualize things that are very, very large. What's it called? The curriculum does a really good job showing a bunch of different examples. When you have like 1,000 different events that could possibly happen, you can imagine that it's going to be really hard to determine what's exactly going on here. But what you'll tend to see, if it's a nice, everything's uniformly structured, you'll see a straight line. If it's more of a bell curve, you'll see kind of like this S kind of slope, where it's like kind of slow at first, and then it'll be steeper going up. Actually, I can annotate on top of this. So let's draw. Yeah. So you can imagine like if I have a uniform function, it'll kind of look like this, going the straight line. But if it's a more of a bell curve Gaussian, you'll tend to see kind of like this S curve, where it's like slow at first and then speeds up and then slow at the end. Okay. So this is kind of how we can quickly look at saying, oh, is it a bell curve? What kind of patterns we have? If you had something else that's kind of strange, where else the probability goes up and then kind of slow again, you'll see this big change, and then it's kind of slow, and then maybe another big change later on. Okay, so again, these things describe the same objects. They're just different ways to show them. Cool. All right, any questions on this so far? No? Okay, cool. So this leaves us to one of my favorite functions, the probability density function. And probability density function is probably the most one you're going to see the most often, because we like to deal with continuous variable or continuous values. So you can imagine here, these have all been discrete, meaning it's only 2, only 3, only 4. There isn't a 2.3. There isn't a 2.7. There isn't a 2.5. Okay, there's only like specific values, discrete. With probability density functions, we can talk about things that are continuous. So I have a couple of pictures on here. So this right here is our PMF. And you can see right here, it's actually on top of that. It's on top of what's it called? A CDF, not CDF, sorry, PMF. And we can see right here is that in this case, we had bins 0 to 400, 400 to 800. So these are more discrete. And our PMF here allows us to have more of a continuous part. So we can say, okay, instead of going from 0 to 400, this part right here, what if I want to talk about just 300? Well, with the PMF, I'm sorry, the PDF, we can actually see, okay, that's our probability that we'd expect. And we can see the probability spikes up and goes down like this. Okay. And again, this is actually using the same data. I didn't make this particularly, but this is how you would describe that same data, binning versus non-binning, right? So there's kind of a subtle point here of why we want a PMF. So let me ask you guys, like, if we had a target going on right here, what's the probability, I don't know if anyone knows, the probability of hitting one very specific point? If I said exactly this dot, what is the probability of hitting that specific little dot on my cursor? Anyone got a guess? Okay, so this is where I would say, like, remember when I said it's either 1 or 0? In this case, you think it's 1? It's 0. Okay, so it's 0. So the reason why it's 0 is because you can think of it like, you know, what's the likelihood of you hitting this exact point? And it's basically like it's nearly improbable. Okay, we can talk about saying hitting a certain amount of area. For example, if it's completely random and we split the target in half, well, half the time you'd hit on the left side, half the time you'd hit on the right side, right? If I split up into quarters, I'd say, oh, a quarter of the time you'd probably hit here. But if we try to make this smaller and smaller, the mathematics work out where it doesn't make sense to hit that 0 point. And the real reason why, you can kind of think of like, why is it 0, like for a physical reason? It basically comes down to the fact that you can always like zoom in. So like the arrow like hit, like, oh, it looks like that exact point, but I can zoom in exactly where that arrow hit. It's like, oh, it's slightly off. And you can kind of think of this going further and further, saying, well, we can't measure things exactly accurately. There isn't something that is an exact number. You can always get like another 0.01 centimeters or 0.000001 centimeters away. You can always get smaller and smaller, so it'll never exactly hit there. So what we can do, we can say, well, any single point is 0, but any area, so if I drew like a little circle around my point right here, so if this is my point that I was talking about, like that little X, okay, like infinitesimally small, that's 0. But I can draw a little circle around it and say, what's the probability of hitting within this circle? And that's how we can actually deal with continuous variables and actually get probabilities that mean something. Basically, we say, is it within from here to here? You know, is it less than X, or it's like less than 3 but greater than 2? And that's our probability range, or our range to hit there. Okay, so subtle point, but I think it's something to be aware of as we go through. Okay, so one thing we do for PMF or PDFs is we'll normalize it an area to 1. So anyone got an idea why we might normalize to 1? I should make that a little more clear. So the area underneath this curve, okay, is always going to add up to 1. Anyone got an idea why we might want to normalize it to 1, so this area is always 1? What do you think that corresponds to in the terms of probability? Well, I should say, what does 1 mean for probability?
100%.
100%, right? So that's actually what's saying is that if we say this area underneath the curve, that area underneath the curve is 100%, is that it encapsulates, it includes all the different possible events that could happen. So that's why we normalize it to 1. It's like, okay, it makes sense to do that. And it makes our math a little bit easier, okay? So, see if I have this example here, oops. So you can kind of see right here is that this allows us to, remember I said about that range? So if I said, oh, rolling, you know, whatever this event spaces from 12 to 14, I can say, okay, what's the probability of getting between 12 and 14? Maybe it's like 11.3, maybe it's 11.2, you know, or not 11, 12.2, 12.3, right, within that range. All we have to do to find the probability is just saying the area underneath this curve, okay? And because the whole area underneath the whole curve is 1, we can just say, oh, okay, that is, if it's 0.13, we can say it's 13%. Okay, and that's why we'll normalize it to 1 for PDFs. Okay, and so I have examples here that show the PDF, the CDF, and in this case, it's the histogram. It says histogram, but it really should be, sorry, it shouldn't be histogram. It should be, I'm blanking right now, PMF, our probability mass function. Okay, so like a little stem and leaf plot. That's more accurate to say. But you can see here, this is the same exact data. So you can see if you break it down with the histogram, okay, for our PMF, that we have some spikes here, some not so much. This might have been randomly generated, for example, and we have this huge spike in the middle. We have our PDF here, this nice smooth curve, okay? And it turns out, we'll find out later, is like, well, how do we find this PDF? And we'll talk about how we actually determine what this is. And then we have our CDF, and if you look really closely, I don't know how well you guys can see it, but if you look closely, you can see it's kind of jagged. And depending on how kind of values you have on, like, maybe, for example, this is not continuous, this is like 0.001, you know, maybe they go up by like 0.1, like 0.01, yeah, 0.01, yeah. Going up that slight amount, you'll see it's kind of like a staircase. But you can see, because it's a Gaussian, or I should say a bell curve, okay, a normal curve, you can see it's got that nice S shape on it. It starts off slow and then swoops up and then goes up to the top like that. This is kind of how you can see these different kind of values all being compared. And it's all describing the same data. Okay, cool. Any questions about this so far? Okay, cool. All right, so now we can do visualizing our PDF. So here. Oh, remember that all our data is discrete, but our PDF is continuous. So like I kind of said before, is that there isn't, like, we can't take continuous data in a lot of ways, right? We always have to make some measurement. You know, we can have like 1.34529 for a value, but eventually we're gonna have to cut off that decimal. We can't have a true continuous value. But our PDF assumes that we can get a continuous value, right? So it's kind of a subpoint like, well, how do we get that? How do we generate this part? So there's a couple ways, and you'll probably see which way makes more sense, or maybe more accurate. So one way is doing the parametric fit. And when I say parametric fit, think parameter. I'm using parameters to basically make this curve. So if we're talking about a Gaussian, okay, which is really what this is, and the curriculum talks about this, all you need to make a Gaussian is your standard deviation and your mean. And if you have those two guys, you're golden. You can make your probability distribution function. What might be the problems of using a parametric fit if I'm using just like this mean and the standard deviation to create this nice bell curve? Anyone got an idea?
What about the outliers?
Exactly, right? So maybe your data, for example, like you can see up here, is that this one's using a parametric fit right here, basically making a nice bell curve. Is our data actually a perfectly good bell curve like this? No, right? You can see there's definitely some spikes up here. You can see over here, maybe we have outliers like Bonnie had said, it could be way out here. Maybe it's actually much more common, but our mean got shifted over here. So our parametric fit isn't exactly the real world in that way. And that's something that can be kind of an issue, especially if our data is not actually normal. If our data is close to normal, or if we think the data, if we had more data points that'd be close to normal, we can probably say, okay, parametric fit makes sense. The nice reason why we like parametric fits is because it's easy. We just need two values and we can figure out the equation. But if it's not or if we don't use a parametric fit, or we think it doesn't make sense for us to try to conform to a Gaussian, we have to figure out a different way, right? And so one way is using a kernel density function. So this is kind of a fun one, is that if anyone, did anyone ever take like physics back maybe like in university or anything like that, where you had to like add up waves together? I don't know if that sounds familiar at all to anyone, but that's what immediately jumps to me, pop up in the background. But basically your KDE, your kernel density function, you can use that to basically figure out, to make this nice, what's it called, to fit your data better. So you can see here, my data is not a bell curve. You can see it kind of spikes up in the middle here, goes down, and then kind of spikes up semi up here, right? So ideally, like you can kind of see on the right here, is that there's this nice kind of like continuous function that goes up like that. But we want to describe that mathematically, okay? So what we can do is essentially make little tiny bell curves around our data points. So remember, our data is not continuous, but it's also not like in a sense discrete, like saying, oh, it's either 1, 1, 1, 1, 1. It might be like, for example, on here might be like, oh, that's like 2.3. Maybe this one's like negative 0.2. And this might be like negative 1.2, okay? So it's not exactly those points. So what we can do is basically make a little bell curve centered right at that data point. And we can do that for each single data point. So you can see right here, that's exactly what's on this right here, is that if I look at this data point right here, I get a bell curve that's perfectly moved around, or sorry, that's centered around this data point. Okay, and if I look at the next data point, you can see there's another little bell curve that's also around that point. And essentially what we do, we make these little bell curves for each of our data points and we add them up together. So if you, again, like if you remember physics at all like this, when you have two waves kind of coming up at each other, when they collide, they actually add up. If there is like a slight, like for example, like you can see on this picture where two of the curves kind of, as they're sloping down, they kind of combine together. They have a little bit of bump, but you can see it's mostly empty versus at this where there's a lot of peaks, you can see it's a much higher peak here. So that's kind of what's going on. And that's what we do for kernel density function. What's nice is that we don't usually have to create these kind of functions. We can use tools that are in NumPy or stats models to basically recreate this for us, so we don't have to do it ourselves. Okay. Any questions on kernel density function? Okay. So again, one of the nice things about it is that it makes us a nice equation we can build out of Gaussians and stuff like that, which are relatively easy to kind of create kind of thing. And you get this much more organic, much more representative of our data versus our bell curve. If we made just one bell curve, it might not be exactly right for our data set. Okay. So you can kind of do a little quick comparison. Is that if this is some random data here, you can see it's roughly bell curve-like, right? With that histogram. And you can see here is that the parametric fit says, okay, let me make a bell curve with that certain mean. Looks like the mean's probably about like 67, maybe 68, okay? And then we have our standard deviation, so you can see it fits it pretty well, but you can see it's not quite true, right? It expects this huge bump up here, but you can kind of see it's much more flat, like in reality for the data set we have. So the kernel density function, right? You see KDE, KDEE. Wait, am I spelling? I can't. Today's off for me, guys. But KDE, that kernel density estimation, if we use that method, you actually see that it fits much better around that data. It's not as pretty as our parametric fit. And by pretty, I mean like a technical pretty, right? Is that this is a nice form that we can quickly do math on. This plot right here, it's nice, but it's not, it's not this nice, really smooth, simple curve that we can describe. So you kind of do some trade-offs on that part. But you'll normally, in my experience, you'll want to do a KDE to better fit your data. But if your data looks pretty normal and you expect it to be a normal distribution, it makes sense sometimes just to do a parametric fit. Okay, cool. All right, any questions on this comparison here? Differences between a KDE and a parametric fit?
So how do you decide like how well you want to fit? Because for KDE, I guess you can use like different parameters, right?
Mm-hmm. So KDE, there's a lot of things you can kind of tweak with it. But one of the things is that between a parametric fit versus that's what you're asking, right, Bonnie? Between parametric and KDE, right? Okay. Usually it comes down to the fact that's like, what do you know about your data? Like, where does your data come from? If your data, for example, if you expanded your data set, you likely would get a normal curve. Parametric fit will probably be just as good as your KDE, like at least in practice. But if your data is not normal, especially like I showed this example right here, is that this is definitely not normal, and we don't have very many data points and stuff like that, then it might make sense to say, you know what, we'll stick with the KDE. to make sure that happens. And again, this is the big part about statistics, in my opinion, is that we use firm numbers and values in tests like this to describe our data. But in the end, it kind of comes down to saying, well, we can apply these kind of like machinery to our data set and get these values out. But it kind of comes down to saying, do these values actually make sense? We can create a parametric fit for anything we want, but it kind of comes down to, well, does that make sense? And sometimes it doesn't make sense. Sometimes it's like, well, it's not quite right, but it's close enough. And if that means that we can spend a lot less time doing computation or a lot less time trying to get more data, it might make sense to say, all right, we'll assume it's a normal curve. And plus you can think too is that maybe the data collection isn't perfect. Maybe there's a slight difference in the instrument. Maybe whatever instrument you're using to collect data, let's say you're collecting like stuff about like the weather, maybe it's not going to be a perfect accuracy every single time. So you have that natural like error. So trying to fit it perfectly with a KDE might not make sense either, because like, oh, well, it's going to have some noise. It's going to have some little variations. So it doesn't make sense to try to keep those variations. Of course, when we collect more and more data, those variations tend to fizzle out. They kind of, basically some are a little high, some are a little low, and eventually it kind of becomes even. Cool. Any other questions, guys? All right, cool. So this leads us a little bit to a normal distribution, which I kind of skipped over a little bit as saying like, oh, parametric fit. But this is where we can talk about that nice bell curve right here, also the normal distribution. And you can see right here, like I talked about before, that green curve right here, it's that nice bell curve. That's what this stuff comes from. So the real reason we use it is from a Gaussian distribution. So you'll hear this used a lot, Gaussian distribution, bell curve, normal curve. Usually when we talk about a normal curve, what we really mean is saying it's a normalized Gaussian. So that means the area underneath it is equal to 1. Gaussians don't necessarily have to be equal to 1, the area underneath, okay? But it's based on the same mathematics. So sometimes you'll hear it being used interchangeably. So again, Gaussian distribution, this is our little Gaussian. And I say, oh, look at this great math. And you might say, Victor, I don't know what you're talking about. That looks ugly. Like, I don't know like what you're talking about. This is not a beautiful thing, but trust me, it is. It's beautiful, okay? You just have to squint at it a little bit. But the main reason why we like these kind of things is because you can see that they're basically, you look at E right here, Euler's number, or I guess I heard Euler, but Euler's number. Right here, E is a number, pi is a number, 2 is a number. If you didn't know 2 is a number, 2 is a number, okay? And then all we have to do is mu and sigma right here. So that's what this is right here. Sigma, mu, which is our standard deviation, and our mean of our population right here. And if we just know these two parts, and of course these are just all constants, those numbers never change, pi never changes, Euler's number never changes, 2 never changes, we can create now a Gaussian. And so this is why it's really nice to say, hey, let's say it's normal curve, because it makes us nice little math and we can just do a parametric fit. And we can just use 2 simple values to make any Gaussian we want, or we can fit any Gaussian to our data, whether or not it actually makes sense. That's what's the danger of it. But if we do have this nice bell curve, again, we have some really great math. For example, we have the 68, 95, then 9 rule. Has anyone heard that before? I don't know, maybe back when you did statistics in high school. Okay, I saw a thumbs up from Griffin. So basically what it comes down to is that if things are a bell curve, or I should say a normal curve, right? Or I should say Gaussian, because it doesn't have to be normal. But basically, if we start from the median, you see right here, X bar, also not the median, sorry, the mean right here, okay? And we go 1 standard deviation from the left, 1 standard deviation to the right, we can see that the values within here from, the mean minus the standard deviation to the mean plus the standard deviation, 68% of all the values are in here, okay? If we extend out another standard deviation to the left and another standard deviation to the right, we have about 95% of our values within this area. And then if we extend another standard deviation out to the left and to the right, we actually get about 99.7% of the standard deviations. This is actually why in a lot of testing, for example, you'll hear this like, is anyone from like familiar with the medical field at all? Maybe a medical field in a past life or anything like that? Okay, maybe familiar, right? So you'll hear people talk about doing like drug testing, you know, or a different kind of treatment and saying, oh, you know, like how good of this drug, like how good was this drug kind of thing. And they say, oh, well, we will do something like, you know, we'll talk about hypothesis testing. And it's like, oh, it's like within 3 standard deviations from the mean. And that means that, oh, we expect that 99.7% of the time, if we didn't try the treatment, we'd get this result or wouldn't get this result. So it allows us to say, oh, well, we're pretty certain then that like you're not just faking it. This treatment's actually working. And 3 standard deviations tends to be the standard. I'm not a biologist, I'm not in the medical field, so don't quote me on that for sure, but it usually tends to be around 3 standard deviations in most of the studies I've seen and what I've heard. For physics or particle physics, does anyone know how many standard deviations they have to get out until they can even talk about it being like a quote unquote, like, oh, this is an interesting, unexpected result? Remember, 3 standard deviation gets you 99.7%. And you can see it gets really, really small, right, as we go another standard deviation out. So in physics and particle physics in particular, if you have 5 standard deviations, it's considered, oh, that seems interesting, but maybe further exploration.
Ooh.
Yeah. And to actually, for the Higgs boson, you guys probably have heard about the Higgs boson recently, in the past, like, what's it, 8 years now, was discovered. Their standard deviation, which was the standard being, oh, you need to have this many standard deviations to actually say it's a new discovery, it was 7 standard deviations, which is just ridiculous when you think about how far that is. Like 7 standard deviations is like all the way over here. Like, it's like how likely that is. If we tried doing 7 standard deviations for a medical test, no drugs would ever get passed. No treatments would get passed. And again, it comes down to situation. In particle physics, they can measure things very, very accurately, and they do a lot of collisions. Like their data is huge amounts of data. So they need to make for certain it's not random chance. For a lot of medical studies, you might have at best like a few thousand people. Like there might not be even that. It might be like only 200 people in your study. So it doesn't make sense to do 5, 7 standard deviations. So again, it's all about context. Anyway, it's good to this nice little rule right here that quickly allows us to do some calculations. Okay. Any questions about our Gaussian normal curve? Anything like that? Cool. Thumbs up if you're feeling it pretty good. Okay. All right. Cool. And again, the curriculum goes through more detail about this in particular, which it should, because you should take more than 45 minutes to 50 minutes going through this. So anyway, so this will lead us to a couple things. So I'm trying to debate right here. So yeah, let's talk about, I'm seeing what time it is right now. Let's talk about z-score. Okay, so z-score kind of basically comes out from the standard deviation. So our z-score basically allows us to calculate how far our value is from the mean, and it measures it in standard deviation. So this allows us to compare different distributions. So for example, this mu and this sigma right here allows us to say, okay, how far is it from the mean, this mu, divided by the standard deviation? And this is what gives us our z-score. And this will be very important when we do hypothesis testing, which again, the curriculum goes into a lot more detail about it. And in fact, I think I put on the very bottom here, just want to jump ahead. Yeah, in this document, Jeff, one of the other instructors, he does a good walkthrough, I think, of doing the z distribution and everything like that. So it's in this file. It's also in the student resources for this section, for section 9. But he does a walkthrough for a whole thing of how you would use a z-test and basically seeing if things are significant. And I kind of did this quick steps of like what a one sample z-test is. But I'm not going to go into full detail right here because it's in the curriculum and Jeff does a good walkthrough for it. Of course, if you guys have questions, you're welcome to ask me for later. But I'm not going to hang on this right now because I kind of want to talk about a couple of other things. Okay. But basically, the main thing you have to know is that the z-score allows us to compare distributions with each other and see if basically a result from one distribution makes sense to the other distribution. I think in Jeff's demonstration in his walkthrough, he talks about a season from one team of NHL hockey versus another team hockey, and seeing if their score, if they are similarly ranked teams or they're in fact significantly different. And that z-score allows us to compare those two parts. Okay. But I did want to talk about the Gaussian. So I have this link right here for a Gaussian. And I think this is a kind of a fun one you can do, is it allows you to kind of adjust the mean and the median. So remember, we always try to normalize it. But you can see as we kind of adjust our mean, we just shift our Gaussian left and right. We can also adjust our standard deviation. You can see our standard deviation will actually get bigger and smaller. And then what's kind of nice about this one I like is that we can actually say, okay, how much is underneath these values? For in this case, from about 1.5 to about 3.5, give or take. Okay, and we can say this area underneath the curve. Okay, and we can actually say, oh, what's this value underneath here? And in fact, we can do our z-score. So our probability, this guy right here, that probability is this area underneath the curve. So if I expand this out to about 2 standard deviations outside, you can see it's about 95%. So the 68, 95, 99 rule. Okay, so you can see that's how we can do this part. You can see there's a z-score here, and this allows us to compare different z-scores between different x values. So for example, this is my first x, this is my second x. Okay, so fun thing to play around with. Again, it's in this notebook here that you can play around. So I do want to talk about a couple things on the normal distribution, because a lot of times you won't get a perfectly good normal distribution. You're either going to have to modify it with transformations, which we'll talk about a little later, or you might see different deviations from it. And so one deviation, obviously we talk about outliers, and this is what kind of leads into skewness. So skewness right here, you can see like positive skew, or in this case, like right skewed. So the skew follows basically where it tends away from the normal curve. So you can see that very middle one, this is a typical normal curve or bell curve right here. The mean, median, mode are all in the center right here. For our positive skew, we'd expect our median to be to the left of our mean. Basically, you can see that this is about, and the median, can someone quickly say, what does the median represent in their own words? When we talk about median.
It's just the dead center of the data set.
Good, and by dead center, sorry,
if it's even, you take the middle two numbers, then divide by 2, and if it's odd, then it's just the one that's dead center.
Right, yeah. So our median basically, thank you, Josh. Our median is basically where 50% of, like, basically where the number of values. So it's like, oh, okay, like we have, 50 values up here, and then 50 values to the left and to the right. So literally 50 of them are to the left or to the right kind of deal. Okay. And that's how we can kind of do that median part. We also have the mode, which is the most common one, but usually we don't talk about that for at least the skewness. At least I usually don't. So this is what you'll typically see. Now, the curriculum actually shows a number. You can actually create a metric for skewness. I actually can't remember the specific one they use, but you'll see that it looks very similar to for variance. So variance, remember it's got the squared power, right? Power of 2. Skewness has a power of 3. And so you can kind of think of like, I like to think about it in this way. Standard deviation is kind of like saying how far out things are spread in one dimension. Skewness, which is third dimension kind of thing, it allows you to think of like things like, oh, how is your standard deviation kind of spread? And then kurtosis, which is kind of a mouthful, but kurtosis is kind of similar to skewness in the way that it's how does the normal distribution differ. And I didn't put a picture on here, but the curriculum does. But basically you can think kurtosis is if I have a normal curve like this, kurtosis might look something, if something's highly on the high end, you might have something that looks something like this. So it's not skewed. It's not, it's not like it's mean or median. It's still a symmetric distribution, but it's more spiky essentially. And so you can actually use another metric to measure kurtosis, and it's something along the lines of the power of 4. I can't remember the exact calculation to be perfectly honest, but it's to the power of 4, and that's because you can kind of imagine like, oh, we have skewness to the power of 3, we have standard deviation to the power of 2. Okay, so basically it's kind of allowing us to measure more information. In this case, it allows us to know what the kurtosis, we can measure, say, oh, this has a kurtosis factor of blah, 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 blah. But one thing I kind of want to note on that is that be careful when you get these hard values when you're doing your analysis. Because people, I mean, I think by nature, a lot of people who go into data science who are statisticians too, we like to be very quantitative. We like to have that value. But note that there isn't like necessarily, so someone asked me, like, well, how do you know when something's, past being skewed? Like it's really skewed, it's like, it's not so skewed, and then it's really skewed. And the way I kind of think about this is there's kind of this age-old problem saying, when does a heap become a heap? So if I put like, 1 grain of rice down, put a bunch of grains of rice down, it's like, okay, it's not quite a heap yet, but I put enough, on there, it's a heap of rice. And it's kind of like, well, when does it become just a pile, like a very simple pile to a heap? And it's not really clear. And that's kind of what kurtosis and skewness is. There's not like a definitive at this value of skewness or at this value of kurtosis, this is when it's now skewed, or this is now when it's, high kurtosis. Okay. So this is where context all matters, is that you as a data scientist, you as the human have to know, well, what does it mean for this data set? If it's like maybe a little skewness might be fine. Maybe skewness actually makes a lot of sense for the data set. Maybe it makes sense that there is a high skew and it doesn't actually mean a bad thing for the data. Sometimes it means, oh, wait, there's something wrong, or this is a very significant result. We need to check this out. So again, this is where context as a data scientist, you have to bring into your values. So basically my warning is be careful not to just state the numbers and just be like, oh, well, the number is this, and therefore I need to proceed in this way. Use the numbers to help guide you and explore further. But it's always important to know what the context is in the long run. Hopefully that's not too confusing with what I said. Cool. All right. Any questions about this? Skewness kurtosis. Again, curriculum has a lot of more, like actually writes a lot more about it, but I didn't want to harp on it because I think it's something, first of all, you're not going to calculate by hand. You'll probably use a package to do that. And it is something to keep in the back of your mind that might help guide you. But honestly, all the times visually, like graphing out your data, plotting it out, you'll quickly see it's skewed or quickly see, oh, it's very spiked up, and you have to decide what to do with that. So let me keep in mind. Okay, cool. So that sounds pretty good. And last thing, I have a few minutes. I did this last time too. I'm going to go through it to it. So I might talk about this a little bit next time too, just to make sure. But statistical testing, I have this in here. And the curriculum does go through hypothesis testing in a lot of detail. And it's a very important thing to understand. But that's why I kind of want to give it enough time, maybe for next lesson, next study group. Okay. But basically, there's an important part of saying, well, okay, how do we know when something, like you might have heard statistically significant. Thumbs up if you ever heard that phrase, statistically significant. Okay, yeah, that's coming pretty much from this hypothesis testing. And just note that there are things like, for example, the null hypothesis, the alternative hypothesis, and our p-value. Those things you'll hear constantly for probably the rest of your career in data science, because they're important parts of basically allowing us to do testing. And if you can kind of guess now, hypothesis, right? Kind of coming from like science in particular, it has a very nice formalism to allow us. And let's see here. I want to make one thing because the curriculum, it hurts me a little bit when I read it. And I've heard other very smart people say it, and I don't agree with them saying it, is sometimes they'll talk about the null hypothesis and the alternative hypothesis, and we'll talk about rejecting the null hypothesis. That's actually your goal, is to reject this null hypothesis. We'll talk more about this. But the alternative, sometimes people will say, like, it's like, oh, we didn't reject the null hypothesis, we can accept the null hypothesis. I'm gonna let you guys know this now. Never say accept the null hypothesis, okay? If you say it, you're dead to me. No, I'm just kidding. But like, I confirmed this with Eli too, because I was a little concerned, like, what's your phrase? And he's like, oh no, it needs to be failed to reject the null hypothesis, not accept the null hypothesis. You failed to reject. And there's a subtle reason why. And I'll just say this last part before I kind of end, is that, for example, for gravity, okay? Gravity, for the most part, pretty sure it works, right? Like, you're not gonna jump out of a building and say, well, I don't know, gravity's just a theory. That's not how we proceed, right? So gravity's pretty well established, but it's possible maybe we find some other mechanism, or maybe gravity's all an illusion in some way, and we just by chance happen to think that it was written this way. Probably not, but let's just pretend that's possible. Our null hypothesis is essentially saying that's like, oh, gravity works, right? If you can try to disprove gravity, if you can find instances where gravity doesn't work, you disprove gravity, right? Or at least the theory of the current theory of gravity, right? You can disprove gravity. However, you could keep like throwing things off like a building and you say, oh, look, it fell down. Oh, it fell down. Oh, it fell down. But if you find that one time it doesn't work, you disproved it, right? Or at least, the idea you disproved the way we think that gravity works. But if you throw 1,000,000 times at this ball, you might be pretty certain gravity works, but you didn't prove that gravity works. Does that make sense? You can be pretty certain that it's true. You failed to disprove gravity, but you never proved it. And the reason why you didn't prove it is because you have to know all the information and know for sure that, yes, in fact, this is complete truth. And in science, in a lot of ways, it's kind of a subtle point. You actually never know for sure. There's always a little hint of doubt. In fact, in science, our whole point is to kind of like disprove things, basically test it so hard until something breaks. That's kind of what we're doing in statistics too. And that's why you never say accept the null hypothesis. You only fail to reject the null hypothesis. Anyway, I wanted to say that because especially the curriculum has a little, says accept. And I was like, oh no. So I found my arch nemesis. No. Just know that you'll hear that sometimes. And in reality, it should be failure. It's like one of those nitpicking things. Anyway, but we'll talk more about, I think I'll save this for next time, which we'll get into linear regression. But I think this is an important part that I will spend extra time on this. And definitely as you go through the curriculum, read that up. Cool. All right. Do you guys have any questions? I know I kind of, it's at 5 o'clock, or is it 5 o'clock for me? So we ran the hour, but do you guys have any questions that you want to ask? You're curious about? Thumbs up if you're feeling pretty good. Thumbs down if you're like, Victor, I don't know what's going on. Sideways, you're like, maybe read some more. Is that that? Cool. All right. That's good. I like thumbs up, but I also like sideways because it means that's like, okay, there's more for you guys to learn. And there it should be a lot more too. So cool. So I'll stop sharing my screen. Oh, I can probably stop recording too.